Students, today we will be talking about semiconductor electronics. All of you are aware of electronics. Each of you every day use some kind of an electronic instrument, electronic device like your mobile, an amplifier or an oscillator or a speaker, mic, radio, TV, all these things these are all electronic devices, and all of these contain some kind of an electronic circuits. So, we will be talking about electronics where you are controlling the flow of electrons. Now, semiconductor electronics. Earlier in 1970s and all, we used to use electronics using vacuum tubes. Vacuum tubes made all the circuits very bulky. You cannot imagine that the computer that you are holding in a hand today was in a room, in a big room, because it used vacuum tubes. So, gradually materials research gave birth to semiconductors. So, semiconductor is the building block of all electronics devices. All electronic components are made up of semiconductor. So, now the question arises, what is a semiconductor? So, in this class what we will be learning is what is a semiconductor, the energy band theory, how you can differentiate between a semiconductor, conductor and insulator, what makes it a semiconductor, why it is called a semiconductor, not a conductor but semiconductor. Then the band theory, then we will go over to intrinsic semiconductors, extrinsic semiconductors like N-type semiconductor, P-type semiconductor. Then we will go to PN junction diode, VI characteristics. So, if possible, we will go over to PN diode as a rectifier. So, these are the things that we will be taking in this class. Semiconductor electronics. And the basic points that we will be covering in this, first what is a semiconductor? What do I mean by a semiconductor? Then the energy band theory, thereafter the basic intrinsic semiconductor, then we will move over to the extrinsic semiconductor, which are impure semiconductor, and among this extrinsic semiconductor mainly the N-type and the P-type. Then when we put these two together, what we get is a PN junction. And how does it behave? Then the PN junction diode means two terminals. So, PN junction diode, the VI characteristic which will include both the forward bias and reverse bias. So, I think in a single class we will be able to complete all these things. So, let us start with what is a semiconductor. Now, if I want to let you know what is a semiconductor, first let us understand what is a conductor and what is an insulator. All these solids that you know, they have a definite volume, they have a definite shape, and the atoms are connected to each other in a certain definite manner. And conductors are the substances that you already know that they conduct electricity. That means electrons can pass through them. That means their conductivity is very high. Whereas insulators like your wood or a plastic, all these things do not allow electrons to pass through. So these insulators have very less conductivity. They do not allow conduction of electrons. Semiconductor is a material whose conductivity lies between these two, between the conductor and the insulator. So if I take the conductor and the insulator, if I measure their conductivity, conductivity is the constant which tells you whether it is able to pass the electrons through it or not. The opposite of that or the inverse of that is resistivity. So we also talk about resistivity. Now resistivity is, so conductivity is 1 by resistivity. So if somebody's resistivity is high, the conductivity is low. Conductivity is very high, of the order of 10 to the power 8 ohm inverse meter inverse. Or in other words, resistivity will be 10 to the power minus 8 ohm meter. If you take the insulator on the other hand, the resistivity is very high, 10 to the power 11 to 10 to the power 19 ohm meter. So if you take the inverse of that, what you get is 10 to the power minus 11 to 10 to the power minus 19 ohm inverse meter inverse. Semiconductor is a substance, material, which lies between these two. The conductivity of semiconductor is within these two limits, 10 to the power minus 5 to 10 to the power 4 ohm meter. If I take the inverse of that, 10 to the power 5 to 10 to the power minus 4 ohm inverse meter inverse. That means conductor does not resist electron flow, 10 to the power minus 8, so less. So the resistivity of conductor is very low, whereas the resistivity of insulator is very high. It does not allow, it opposes the current flow. Whereas the conductivity of conductor is very high, 10 to the power 8 ohm inverse meter inverse. Insulator is 10 to the power minus 11 to 10 to the power minus 19. This is very low value. So the conductivity of insulator is very low, it never conducts. It does not allow current to pass through. Whereas semiconductor lies in between these two. Normally at room temperature it does not allow current to pass through, but by suitably we can change the conductivity of a semiconductor. And you cannot understand how semiconductor can be used for all electronic instruments, all, whether you talk about a chip, you talk about a integrated circuit, you talk about a TV motherboard, computer motherboard or a TV motherboard, anywhere. Without a semiconductor these things cannot be made. So the semiconductor, that means what we get from this discussion, we find out that semiconductor is a material whose conductivity, this is a material whose conductivity lies between that of the conductor and insulator. Let us see how such a material, what is that kind of a material. For example, if I give an example, we have the germanium crystal, Ge for the germanium crystal, or these are the simplest of them, and silicon. Germanium with atomic number 32 and silicon with 14. So if you draw the electronic configuration, 14 will be 1s2, 2s2, 2p6. So you have 6 to 8, 10, 4 are left out. So 3s2, 3p2. So there are 4 electrons in the outermost orbit. Whereas in case of germanium, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2 and 4p2. So in the 4th orbit there are 4 electrons which are in the valence electron or the outermost electrons. So let us see how this property, the 4 electrons in the outermost orbit, or you can say that these elements, these are tetravalent, or the valency is 4. Their valency is 4. 4 number of outermost electrons. So let us see how germanium and silicon are semiconductor, and why we say that at 0 K or at 0 K they do not conduct, but if the temperature is more, they can conduct, or if you add some impurity, they can conduct. So let us move to what is a germanium. So how we distinguish? We are talking about the germanium, and we know now that what is a semiconductor. But to explain it from the band theory, we must talk about energy band. How the energy band of semiconductor is different from the conductor and insulator, and how it can be made a conductor. Now, before going to energy band, all of you are aware of energy level. When you have a single atom and the single atom has some electrons in it, let's say hydrogen has 1 electron, so you put 1s1. So that every electron in an atom has been given a permitted energy level. They have certain energy they can acquire. So from Bohr's atomic theory, all of you know that every electron is to be put in a certain permitted level. The energy of these permitted levels are already defined or given by formula, it is given. That means the electron can acquire only that much amount of energy, not anything in between. So we can draw energy level diagram. You draw energy level diagram like this is, let's say for hydrogen atom, this is minus 13.6 electron volt, the first ground state, first energy level, then the next level minus 3.4 electron volt, and so on. So you draw energy level diagram. You say that these are the energy levels, first energy level, second energy level, and so on. So when it is a single atom, we talk about energy level, but what happens? What is the energy band? What happens when atoms come closer? Many atoms. There are many atoms like in a crystal. So when these atoms come closer, electron of each atom is affected by the nuclei as well as the electrons of the other atoms. See, there are many atoms in a crystal, numerous atoms together, not a single atom. So the electron of first atom is influenced by the second one, third one, fourth one, and all. So as a result of which the energy of a certain electron changes because it is affected by other nuclei and other electrons. So even if there are n number of electrons, all having the valence band, certain valence energy level, what happens that when the atoms come closer, each electron is affected by other nuclei and electrons. Nuclei of other atoms, that means. So as a result of which each energy level now, you cannot talk about energy level anymore, because now this energy value of a particular, let's say the 3s electrons. 3s electron of, there are n number of atoms. 3s electron energy of one electron now changes. Second one slightly other than that. Third electron, 3s electron of third atom may be something little different. So that means the same 3s level of an atom, of an electron now may have different values now. So, or we say that each energy level now spreads or splits, we can say, splits into many levels. It can have different values now. So, one single level now spreads into many levels. So, we say that one single level now may have these values, these are the possible values. And these energy levels, each of that means one electron can have this value or may have a slightly less than that or less than that, like this. So, each energy level now splits into many levels, and these many levels, that means they are very close to each other. So, they appear to be continuous. So, they are close energy levels, these are very close levels, and they appear to be continuous. And now we cannot talk about a single energy level because they are very close by. So, as a result of which you cannot say that this is one, this is different from this. So, what we say is a total band of energies. These are the all possible energy values which are very close. So, we talk about what it gives rise to an energy band. So, what is an energy band? Energy band is the spread of energy that an electron can have when many atoms are grouped together in a crystal, in a solid like this. So, this is how it gives rise to an energy band. Now, out of these energy bands, that means every layer, 1s, now it becomes a band of energies. 2s, again a band of energies. The 2s electron of atoms can be in all these bands. So, what we are more concerned about is the valence band. The valence band, as you know, the valence electron means the outermost electrons are called valence electrons. So, valence band is the energy band which contains, which includes the energy levels of the valence electron. Of the constituent atoms. In a crystal, in a solid. So, when there are many atoms, you are talking about many energy bands. Now, the valence band is the last band, that means the last band which contains electrons, because those are the outermost electrons. Now, this valence band, this may be full, completely full, or partially filled. It is never empty because it is the outermost electron, it will contain the outermost electron of the atoms, constituent atoms, so it is never empty. The conduction band, however, is the band of energy which lies just above the valence band, the next band. That means the valence band is the outermost electrons band, whereas the conduction band is the energy band just above or beyond the valence band. Now, that means if an electron is present in the conduction band, you can say that it is beyond the outermost orbit. That means it is free. It is not attached to the atom. It is in no way connected to the atom. It is free now. So, the free electrons are in the conduction band. And if a material has free electrons, means it can conduct, because it is that electron can move from atom to atom. So, such a thing is a conductor. So, in conductors, at normal temperature, you will find that there are many free electrons, and you will find free electrons in the conduction band. So the conduction band is either partially filled, maybe empty, or partially filled. And if an electron is present in the conduction band, you are sure that that material can conduct. So we have valence band and conduction band. Between these two, the energy difference is called the forbidden gap. So forbidden energy gap this is the separation of energy of top of the valence band and bottom of the conduction band. This is called the forbidden energy. For example, if you have, this is my conduction band, this is my valence band, electrons are present in this valence band, there are many levels in the valence band, no electron in the conduction band, this separation, this is my forbidden energy. Why forbidden? Because no electron can have any energy value in that levels. You cannot have some energy, an electron which has an energy value up to this, here or here or here, you cannot have. It is forbidden. That region or that level is forbidden for an electron. So that is why it is called forbidden energy gap. So on the basis of this, how we can distinguish between a conductor, insulator and semiconductor. So if I take the conductor and draw the diagram of the energy band diagram, what we will see is something like this. Let us say this is my valence band from here to here. The valence band has some electrons like this. This is my conduction band. From A to B is my valence band. The conduction band is from, let us say, from C to now D. So C to D is my conduction band. What do you find? If this is my conduction band, there is no separation between the conduction band and valence band. Valence band and conduction band, they overlap. What do you mean by overlapping? Overlapping means some electrons, for example, these two electrons here, these two electrons are also present in the conduction band. So for all time to come, there is always some electrons which are present in the conduction band. So in the conductor, what is the main criteria we find? That there is overlapping of these two bands, overlapping of valence band and conduction band. There is no separation, there is no forbidden energy. What about the insulator? If I go to the insulator and draw the same diagram, the conduction band and valence band, what we find that the valence band ends here. This is my valence band. The conduction band starts from here and let us say from here to here. So C to D is here, A to B is here, no overlapping. In fact, the forbidden energy gap, this energy gap is greater than 3 electron volt. In fact, it is more or less 10 electron volt. Much more than 3 electron volt. So such a large separation of energy, if an electron is present here in the valence band and you want to make it free, because conduction will take place only when electrons are, mainly when electrons are present in the conduction band. So what you want to do is to take this electron from the valence band to the conduction band. But to take it from here to here, you have to give at least 3 electron volt energy, and this is quite a lot of energy. By no means can you supply it 3 electron volt energy, and hence insulator remains insulator, it never conducts. even if you try to take some electron from the valence band to the conduction band, which is not possible. An insulator never conducts. So here the forbidden energy gap, this forbidden energy gap is very large, is greater than 3 electron volt, large. This is a large value. If I take the semiconductor, on the other hand, the semiconductor, if I draw this diagram, the energy band diagram, the valence band here, the conduction band here, this gap is now less. It is less than 3 electron volt. So, such a small energy, by some means we can supply this much of energy to an electron which will go from valence band to conduction band. So, once it goes to the conduction band, it will be free, and once it is free, it can conduct. So, this is how a semiconductor, even though it does not conduct at normal temperature at 0 K, it can conduct if you can supply it enough energy to transfer an electron from the valence band to the conduction band. So, this is the difference between conductor, semiconductor and insulator as far as the band theory of solids is concerned. There is a overlapping in conductor, always some free electrons. Insulator, the difference between the conduction band and the valence band is very large. The forbidden gap energy is more than 3 electron volt, so it cannot conduct. By no means you can make it conducting. Whereas semiconductor, this forbidden energy is small, of the order of 3 electron volt or less, and hence you can convert it to a conductor. So, it can conduct electricity under proper circumstances. So, let us see how we can make it conducting. Now, the intrinsic semiconductor, or which is a pure form of semiconductor. When you have a pure form, this is a pure semiconductor. The purest form of the semiconductor is called intrinsic semiconductor. So, for example, I will take the case of germanium crystal, let us say. As I have already told you, germanium crystal has 4 electrons in the outermost orbit. So, let us draw the germanium. Suppose I have a germanium crystal, there are many atoms grouped together. Let us say germanium, there are many germanium atoms, each germanium atom is surrounded by other germanium atoms, and each of them have 4 electrons in the outermost orbit. So, let us see what will happen. Now, to obtain the octet, you know the octet rule from chemistry, that an atom is satisfied when it has 8 electrons, hydrogen of course 2 electrons, but let us say the 8 electrons octet theory. Then if in a germanium crystal many germanium atoms are near each other, they are surrounded by germanium atoms all together. So, each of them has 4 electrons. So, what it can do is they can form a covalent bond between the nearest germanium, so that there will be 8 electrons now, another germanium here. So, this central one, you can see that it has formed 4 covalent bonds with the nearing germanium atoms. So, each of them form 4 covalent bonds. So, this is how these are covalent bonds are formed between the neighboring germaniums. Each of them form 4 covalent bonds. So, germanium, next germanium, next germanium, all of them on all sides 2 bonds. This is 1 covalent bond, 4 covalent bonds. 8 electrons 1 2, because this electron now will be, there is a mutual sharing of electrons in a covalent bond. So, this electron will also be counted for this germanium. So, now each of them are satisfied. So, this is the situation at 0 K. So, now question arises, there are no free electrons. So, this cannot conduct electricity because it is all satisfied. There is no way, if I supply it some electron, that electron will not go. If I make a material, make some metallic contact and connect it to a battery, battery will supply it electron, but that electron cannot go inside because there is no place. all these germanium atoms are satisfied, they don't want to take any more electron. So this will not conduct. At 0K, it will not conduct. Now then what happens? So intrinsic semiconductor is, the valence band of intrinsic semiconductor is completely full. There is no vacancy and there is no free electron in the conduction band also. So it does not conduct. But if I supply it some energy, in the form of heat, let's say the temperature increases. For example, if temperature increases. Now when temperature increases, there is a possibility that, let's say, this covalent bond breaks. Now when this covalent bond breaks and an electron goes out, because it has more energy, it vibrates and it breaks the covalent bond, it goes out. When this electron goes out, the bond breaks. This place is a vacancy. So this vacancy, I will call it a hole. The vacancy created from where an electron has gone is called a hole. Now this electron, if I take the band theory, what has happened, that this is my valence band. If I draw the band structure, this is my conduction band. One of the electron breaking a covalent bond means one of this electron has gone to the, you have supplied it enough energy, so it has gone here to the conduction band. So here there is a vacancy now. There is a place for another electron to come. So what will happen, that as soon as you connect it to battery or by some other means, this place गोटे जगह खाली अच्छी अन्य इलेक्ट्रॉन माने चाहिए सेठी जीवा पाई, so naturally other electrons will try to go there. So what will happen, let's say that this bond now starts breaking and this electron from here goes to this. So what happens, that this place will be now filled and this will form a covalent bond, but the hole is now present here. So this is what happens. Now this can continue. Suppose this will take the electron of this germanium. Let's say this germanium, this electron will go from here to here. So that means this covalent bond break and here there is a hole. So the hole has travelled from this germanium atom to this germanium atom to this germanium atom. In fact, electron has gone from here to here, from here to here, because it started with the breakage of one covalent bond. If one hole is created here, now some electron of the other atom will go to fill this place. When it will fill up that place, the hole is created in the second atom. So that means hole is not a particle, it is just a vacancy where there is a tendency of other electron to come. But it moves from atom to atom as if there is some particle which is moving with a positive charge because it is attracting electron. So that is why even though it is not a particle, it is a vacancy, but it has a tendency to attract electron because electron tends to go to that empty space. So that is why hole is treated as a positive charge. But remember, it is not a particle. It is not a particle like a proton. Proton is a positive charge, but it is not a, it is a particle. Hole is not a particle. It is just a tendency to attract electron. That is why we treat it, we read it as a positive charge because the electron can move there. So in this manner, hole move from place to place and hence it can conduct because electrons are now moving from atom to atom. So we say that now it is conducting. So the intrinsic semiconductor, which is a pure semiconductor, can be made conducting. At 0K it is not conducting because there are no free electrons, but it can be made conducting by giving it a small amount of energy more than the forbidden energy. Like for example, you need for a germanium you need 0.7 electron volt and for a silicon you need 1.1 electron volt. That means the forbidden energy gap for silicon is 1.1 electron volt, for germanium it is 0.7 electron volt. So if you give this much amount of energy, an electron can go from the valence band to conduction band, and now it is conducting. And holes move from atom to atom by breaking the covalent bonds. So this is, and because holes are vacancies which can attract electron, we call it a positive charge. So hole is treated as a positive charge. So in this case of intrinsic semiconductor, as temperature increases, the number of breakage of covalent, each covalent bond when breaks produce one electron and one hole. So there are electron hole pairs. Electron hole pairs, they are produced in pairs. Any covalent bond breaks, an electron is free, made free, the place from where it is going, there is a hole. So electron and hole pair, here is an electron, correspondingly there is a hole here. If another electron goes from here by getting energy, there is an electron here, but this place there is a hole. So you can see that pair of electron and hole. Electron hole pairs are created in an intrinsic semiconductor when the temperature is increased. But what we find that the conductivity is still less, is not very large, conductivity is still very less. Although we can make it conducting, the conductivity is not like a conductor, so that we can manipulate it or we can do something with it. That is why the intrinsic semiconductor conductivity is less, but we cannot use it for any practical purposes. So how we can still increase the conductivity of intrinsic semiconductor? That is an extrinsic semiconductor. Now extrinsic semiconductor are two types. It may be an N-type semiconductor or it may be a P-type semiconductor. Why they are N and P type, that I will tell you. So when impurities are added, impurities, not only simple impurities, suitable impurities. Suitable impurities in calculated amount or in suitable amount are added to an intrinsic semiconductor, we get an extrinsic semiconductor. So when you add the impurities, this process of adding is called doping. The process of adding impurity is called doping. The material, the impurity is called dopant. This is the impurity. The impurity atom which is added is called dopant. So when depending upon the type of impurity, you get a N-type semiconductor or a P-type semiconductor. So let us first take how we get a N-type semiconductor. Now I have already told you that these intrinsic semiconductor belong to the group 4 elements or tetravalent. They contain 4 electrons in the outermost orbit. Now we can add the impurity either pentavalent impurity or trivalent impurity. Pentavalent means those atoms which have 5 electrons in the outermost orbit. Trivalent impurity, those have only 3 electrons in the outermost orbit. Accordingly, you will have, if you add a pentavalent impurity, you will get a N-type semiconductor. If you add a trivalent impurity, you will get a P-type semiconductor. So here the dopant is a pentavalent impurity. Pentavalent impurity, like we can have arsenic, antimony or phosphorus. All these are pentavalent impurity. So they have 5 electrons in the outermost orbit. So what will happen now? If earlier I had drawn the germanium crystal in which each germanium atom is surrounded by another germanium atoms on all sides. Now what happens, that when you add, this impurity is added in a very small amount. It is hardly less than 1% of the atoms of the original intrinsic semiconductor. So because you are adding only a few atoms of phosphorus or arsenic, you say germanium is replaced by, let us say, by phosphorus. I am adding the phosphorus impurity and it replaces one of the germanium atom, let us say. It will be surrounded by, there is every chance that phosphorus is not surrounded by phosphorus because there are only a few atoms you have added. So the number of germanium atoms are more. So in any phosphorus atom goes, impurity goes, it will be surrounded by the germanium atoms only. So now it is surrounded all around by germanium atoms. How it will form covalent bonds with the nearby, that we want to see. What happens to the covalent bonds earlier made between the germanium atoms? So in this case, there are 5 electrons of the phosphorus. Phosphorus has 5 electrons. So 4, it is surrounded on all sides by 4 germaniums. So it will form atoms, covalent bonds, 4 covalent bonds with the nearby germanium. This 5th electron is unwanted now because phosphorus wants to have 8 electrons in the outermost orbit. The theory says that every atom will be satisfied if it has 8 electrons in the outermost. So now by forming 4 covalent bonds, it has now 1, 2, 3, 4, 5, 6, 7, 8. So 8 electrons it has already got. This is the 9th one. Naturally 9th one will be unwanted. So the phosphorus atom wants to get rid of that electron. So what happens, that all these germanium atoms are as before. You have already drawn this diagram. So as before, these are the atoms, all are satisfied. But this electron is now loosely bound, I can say, by only a small amount of energy is required to leave it. So by giving hardly, in this case, in case of germanium, you will hardly require 0.01 electron volt. By giving this much amount, this electron will become free. But see, this electron from where it goes will not create a hole. Why? Because there is no tendency, even though there is no vacancy in kind of thing. It is an unwanted thing which has gone away. So there will be no vacancy. It will not be that place will not have a tendency to attract an electron. No electron will want to go here. So there is no hole. Only that this has come from the phosphorus and has become a free electron in the lattice. So this is what happens in N-type semiconductor, that electrons are produced, free electrons are produced, because now to the conduction band, valence band, now the pentavalent impurity has an energy value somewhere here, the outermost orbit of the donor, because it donates, so donor level. The energy value of this 5th electron has value of this much. It is only slightly less than the conduction band. This is 0.01, I said. So by giving it that electron, the 5th electron was here. Now this electron has gone from here to here. By getting 0.01 electron volt, it has gone to the conduction band. So now free electrons are produced. Jeteta impurity atom jaithibo setikita free electron will be produced. So that many free electrons are produced in the conduction band by giving only this much amount, 0.01 electron volt of energy. In the earlier case, in the intrinsic semiconductor case, we saw that we have to give at least 0.72 electron volt to make it conducting. Here you require so small amount of energy. So this goes to this. So this is how N-type semiconductor is produced. Why N-type? You mark this, that because in this case the electrons are the main majority carrier. Why this majority carrier? See, in case of an extrinsic semiconductor, if the temperature is more due to the thermal generation of some electrons will be thermally activated and they will go from valence band to conduction band, just like the intrinsic semiconductor. So pure semiconductor case रे जहाँ होउथिला सेया तो हबो ता सहित we find that the impurity atom produces extra electron. So in case of intrinsic semiconductor there was electron and hole pair, jeteta electron setikita hole produce होउथिला. Now in addition to that we have extra electron from the donor atom. So now the number of electrons are more than the number of holes. So both are present. Electrons are present. How electrons are produced? One, by the thermal generation, by thermal breakage of covalent bond. Covalent bonds are breaking all the time. So that is as temperature increases. So due to thermal generation, an electron is produced and a hole is also produced. In addition to that, each of these impurity, now they are the donor atom, they donate an electron. That is why they are called donor atoms. So the impurity here is called a donor atom. The donor atom also gives electron to the conduction band. So this, if you give that energy, it will go to the conduction band. So there are more number of electrons than the holes. Holes are only because of the breakage of covalent bond at high temperature. So in this case, the majority charge carriers, majority carrier are electrons which are produced by two means, one from the donor, one from the breakage of covalent bond like the intrinsic. And the minority charge carrier, because they are less in number, that is why they are called the minority carriers. The minority carriers are holes, they are less in case of N-type. And conduction takes place mainly due to the majority carriers, which are electrons, which are negative N, that is why it is called a negative N-type semiconductor. So the N-type semiconductor has more electrons, electrons are majority carriers, holes are minority carriers. The dopant is a donor atom, it donates an electron to the conduction band, and the conductivity is quite high. By giving only a small amount of energy, you can make it conducting, and it is called N-type because the majority carrier, the main conduction of electricity takes place because of the negative electrons in the crystal. Let us see about the P-type semiconductor. So similarly, now once you understand what is a N-type semiconductor, you can yourself build up the P-type semiconductor. In the P-type semiconductor, we may have trivalent impurity. So the impurity here is trivalent, 3 electrons in the outermost orbit. So this is the dopant is, or the impurity is dopant or impurity is trivalent, like indium, boron. So now place, instead of the phosphorus P, now let us put one B in the middle, the boron atom in the middle, which has only 3 electrons, and it is surrounded by germanium atoms all 4 sides. I am not drawing the entire diagram, you complete the entire diagram. So now you see that the 3 covalent bonds are made, completed. All other germanium, they are bonded to each other by 4 covalent bonds. So you complete this diagram. and this carries on. But what happens now? There is a hole, you can say. There is a need of an electron there. If there is an electron, then only the fourth covalent bond can be made. So there is a hole created. Ape ape tamane seti gote vacancy create hala. There is a tendency this boron atom now will try to pull an electron from other atom. So this electron, this covalent bond will break, and what will happen, that this electron has gone now here to fill up this place, and here is a hole now. So the hole and the covalent bond will be completed. So because boron has a vacancy, it is trivalent impurity, it has 3 electrons, it needs another electron to complete the covalent bond. It will try to take an electron from somewhere else. So this germanium atom electron now tries to go to complete this vacancy. So it goes to that hole, but the hole is now shifted to this germanium atom. So hole is moving from atom to atom and this way. So in the band structure, what we find, that this is my conduction band, this is the valence band, the boron now here B boron atom is an acceptor atom. In the case of N-type semiconductor, the impurity was a donor atom. This is a donor atom. But here the impurity boron atom is accepting an electron. So the acceptor atom energy level lies somewhere here. This is the acceptor atom level, acceptor level. So an electron from the valence band will go to this. Now this difference is also 0.01 electron volt. So the valence band, from the valence band, an electron can go to the acceptor level energy band, and hence here there will be a hole. So electron will appear here, and the valence band there is a hole there. Similarly, as in the case of N-type semiconductor, in this case also some electron and hole pairs, electron here and hole are produced. This is because some electron has gone from valence band to conduction band. This is due to thermal generation. Thermal generation of electron hole pair always goes on. If the temperature is not 0 K, there is always a electron and hole pair created. So in addition to that, what we find, more number of holes are created. The acceptor atom, the number of acceptor atom, or you say boron atom, the impurity atom, as many as impurity atoms are there, that many vacancies are created, and those are the holes. So number of holes here is more than the number of electrons in the conduction band. So here we have number of holes are the majority carriers. So the majority carriers are, in this case, the majority carriers are holes, and the electrons are less in number. Electrons are minority because less in number. So because holes are treated as positive charge, P for positive, so that is why it is called a P-type semiconductor. So what we find, that in case of N-type semiconductor, dopant is pentavalent. In case of P-type, dopant is trivalent, or the impurity is trivalent. In the case of N-type, the impurity is a donor. It donates an electron to, because it has 5 electrons, it can form 4 covalent bond. 1 electron is extra, so that extra goes away, it donates to the conduction band. So it donates an electron. Majority carriers are negative electrons, that is why N-type. Minority carriers are holes. In case of P-type semiconductor, the impurity is trivalent, like boron and or indium. In this case, boron has 3 electrons, so it can form 3 covalent bond. It requires another electron to complete the 4th covalent bond. That is why there is a vacancy there. There is a hole there. So that hole is created, comes from the electron to that hole goes from another germanium atom. So holes move from one atom to another atom, and in this manner it can conduct. The impurity atom here is an acceptor atom. because it accepts an electron. Boron here accepts an electron, that is why it is an acceptor atom, and the acceptor atom energy level is just above the valence band. The donor energy level is just below the conduction band. That is the difference. Here it is up above, here their valence acceptor level is just above the valence band, not near the conduction band, here near the acceptor level. The majority carriers are positive holes, and that is why it is called a p-type semiconductor, and minority carriers are electrons. So from this discussion we know that whenever we have n-type semiconductor, there are more number of electrons, there are few holes present. In a p-type semiconductor, there are mainly holes, more number of holes, less number of electrons. So what happens when we grow a crystal, one side of which is a p-type and others is a n-type? Not that you bring a p-type semiconductor, bring a n-type semiconductor, put them together. That is not a atomic level junction. Junction means it is metallurgically it is made. While making the crystal, one side is given p-type impurity, the other side is given n-type impurity. So they are close in contact, atomic contact between the atoms. Not that you bring a p-type, bring a n-type, just put them together. It is not a p-n junction. So p-n junction, what happens when this p and n are together present in a single crystal? So that gives us the p-n junction, a p-n junction. So a single crystal in which one side is p, the other side is n. Both have the same width, let us say. And I have already told you that these have mainly holes, are majority, and minority carriers are electrons. In this case, the majority carriers are electrons and minority carriers are holes. What happens when such a single crystal is made with p side and n side? Now, first we find that the concentration of holes is more here, less here. They are minority here, majority here. That means from here to here, from p to n, there is a decrease in the concentration of holes. So concentration of holes decreases from p to n. And similarly, concentration of electrons decrease from n to p, because here there are more number of electrons, less number of electrons here. So the concentration gradient, so due to this concentration gradient, there will be diffusion of, just like gas molecules diffuse from higher concentration to a lower concentration, diffusion of holes takes place from p to n, and diffusion of electrons from n to p. Does it mean that all the electrons of the n side will come to the p side and all the holes of p side will go to the n side? No. What happens? There will be some mechanism starts. Now let us say that one hole has come from here to here and one electron has come from here to here. If an atom is left, one electron has left the atom from n side, then that atom will become positively ion. So that becomes positive ion. So what happens that because now it has lost an electron, गोटे इलेक्ट्रॉन जदि पलि जीव तबे नेचुरली तार न्यूट्रल थिला बर्तन से पॉजिटिव हो जो लेस इलेक्ट्रॉन हैला सो दैट एटम बिकम्स एन आयन. So what happens that because electron has come from n to p, जोठू इलेक्ट्रॉन बाहरी गला से एटमटा आयन हो जिवो पॉजिटिव आयन, जोठू होल गोटे आसिला सेटा गोटे नेगेटिव आयन हो जिवो. So in this case there will be positive ion on n side of junction, and similarly negative ions, the atoms जो थ्रू कि गोटे नेगेटिव इलेक्ट्रॉन पलैची सी पॉजिटिव आयन हो गला, जो थ्रू गोटे होल पलैची एन साइड को सेटा नेगेटिव आयन हो गला. सो नेगेटिव आयन्स ऑन पी साइड ऑफ द जंक्शन. सो अ लेयर ऑफ positive ions on n side of the junction will be produced and a layer of negative ions in the p side of the junction is produced. So this is what happens due to diffusion. This is the diffusion, and we say that the flow of diffusion of holes from p to n and of electrons from n to p, these produce a diffusion current. तामाने इलेक्ट्रॉन याड को डिफ्यूजन है, इलेक्ट्रॉन डिफ्यूजन करंट, and from here to here whole diffusion current. But current ro direction जदि दबाई, because they are oppositely charged, electron ro diffusion जदि left right ro left को होची, the current will be in the same direction. तेणु दीटा actually current मिसी जिबे. So diffusion current, total diffusion current is from P to N. So total diffusion current will be from P to N. But what happens now? The second thing that happens after these holes and electron have changed the places, diffusion hela pore, what happens that this is positive ions on n side of the junction and negative ions on p side of the junction are created. This is created now. Now you know that whenever there is a positive charge and a negative charge, there will be an electric field from the positive charge to the negative charge. So that means it will create an electric field. Electric field from n side of the junction, n side to p side of junction. So there will be an electric field from n side to p side of the junction. Then what will this electric field do? Now electric field, if you have a positive charge here which can move, and there you apply an electric field, the charge will move in the direction of the positive electric field. So a positive charge moves in the direction of electric field, a negative charge moves in the opposite direction of the electric field. Here this positive charge is an ion, it is fixed to the atom, it is fixed to the crystal, so it is not mobile, it is immobile, it cannot move. But this electric field will allow the minority carrier, here there are some holes present, these holes are positive and these holes are minority carriers, they are mobile, they are not immobile like the ion. So these mobile minority carriers, so the mobile minority carriers, that means which are the mobile minority carriers? The minority carriers are holes in N and electrons in P. These are minority in number, they are very less in number. So these mobile minority carriers can move, their motion is aided by the electric field. Motion of mobile minority carriers is aided or supported, is supported by electric field, supported by this electric field at the junction. So what it will do? It will, that means electrons from P to N and holes from N to P will move. By the help of electric field. And this produces what is called drift current. Another thing this field does, not only it produces, means what happens that this field will not allow the electrons to go from N to P, does not allow this E field, that electric field at the junction does not allow electrons, that is majority carriers, to go from N to N, N to P. It also does not allow holes to go from P to N. That means it does not allow the majority carriers to change their position. That means holes are not obstructed from P to N and electrons are obstructed from N to P. Because it opposes the motion of majority carriers, it is called a barrier field. So this field opposes motion of majority carriers, and that is why we call it barrier field. It is a barrier. It opposes. It is like a wall achi. It is not allowing the majority carriers to cross the junction, but it supports the minority carriers to cross the junction. The minority carrier produces a drift current. The majority carrier initially produces a diffusion current. These two currents at normal temperature or at 0 K, these two currents, next 7th, these two currents, that means the diffusion current becomes equal to drift current and an equilibrium is established. So stops, everything stops. That means a field is created, but majority carriers already, as soon as an electron from here goes to this place, that will be pushed back to this because of the electric field. Electric field supports the motion of electron in opposite to itself. So if an electron goes from here to here, majority carrier cross from here to here, the same thing will be again pushed back to the N. So everything stops and PN junction does not conduct. If you connect it to an external circuit just like that, it will not conduct because across the junction there is a field, or this is called barrier field, and the region in which this region in which these ions are present, and this place, this region is devoid of any mobile charge. And that is why it is called, because these ions are immobile. They cannot move from across the junction. So the region which is devoid of any mobile charge is called depletion region. Because it is depleted of all the mobile charges, that is why it is called a depletion region. And there is a barrier field at the junction, there is a depletion region. The depletion region of the order of, it is 0.5 micrometer thickness. This is the thickness or width is that order. It is of that order. So this is what happens in a p-n junction, that initially some electrons majority carrier from n to p goes, some holes go from p to n, but once they go, some of these atoms now become negative ion on this side, on the p side, and positive ions on the n side of the junction are deposited. This, after that, this will produce an electric field. Now this electric field will not support the motion of majority carriers. That means it will not allow electrons to go from n to p, it will not allow holes to go from p to n. That is why it is called a barrier field. The thickness of the junction where there are no mobile charges is called the depletion region, because it is depleted of all the mobile charges. That is why it is called depletion region. And this junction has a barrier field. It will not allow the majority carriers to cross, and the barrier field will have the corresponding potential is called barrier potential. Corresponding potential, barrier potential. The barrier field has a barrier potential. So a p-n junction is like this. It will have, that means it has a barrier field at the junction. This barrier field has a barrier potential. That means if any charge wants to move, it has to overcome that barrier potential. There is a depletion region at the junction. At the junction there is this thickness where there are no mobile charges. So the depletion region is actually something like a barrier, and there is no motion, no free, no conduction. So p-n junction is like this. How do we make it conducting then? To make it conducting, we have to connect a biasing, or a voltage must be given from external circuit, so that this depletion region decreases, this barrier potential decreases, and electrons or the majority carriers can cross the junction. So in the next class, we will move over how we are going to use a p-n junction diode and what are its characteristics and how it can be used to create a rectifier. Thank you.